Readings of two wattmeters connected to measure power in a balanced three-phase load is 5:3. So W1 by W2 is equal to 5 by 3. Now what is the power factor of the load? Power factor of the load cos phi is given as cos of tan inverse of root 3 into W1 minus W2 divided by W1 plus W2. Now I can write this one as cos of tan inverse of root 3 into W1 by W2 minus 1 divided by W1 by W2 plus 1. So what he has given? W1 by W2 ratio as 5 by 3. So this is cos of tan inverse of root 3 into 5 by 3 minus 1 by 5 by 3 plus 1. So this is cos of tan inverse of root 3 into 5 minus 3 is 2 divided by 5 plus 3 is 8. So this is 1 by 4. You will get it as 0.917. Now how to decide whether it is lagging or leading? In this denominator, if you have plus sign, positive sign, then it is lagging, negative sign, then it is leading. Okay, so since we have positive sign in this part, okay, so this is 0.917 lagging, that is option A is the correct answer.
Loop gain of the op amp is 92 dB. The gain error of the amplifier is, here the amplifier given is here the gain error is defined as ideal closed loop gain minus actual closed loop gain divided by ideal closed loop gain. That is, ideal closed loop gain is 1 minus beta and the actual is AOL 1 plus AOL beta divided by 1 by beta. So if we take 1 by beta as a common, we will get this as 1 minus AOL beta divided by 1 plus AOL beta, which is 1 by 1 plus AOL into beta, which is into 100. If we will get this as 0.0275%, that is option B is correct.
Find the value of lambda for which the given equations are consistent. So the given equations are x plus y plus z is equals to 6, x plus 2y plus 3z is equals to 10, and x plus 2y plus lambda z is equals to 12. Now, in order to find the value of lambda, what we do is we'll make the coefficient matrix, determinant of the coefficient matrix to 0. If the determinant of the coefficient matrix is 0, then the equations will be consistent. So the coefficients are 1, 1, 1, then 1, 2, 3, 1, 2, lambda is equals to 0. Let us apply row operations. We'll apply R1 tends to R1 minus R2 and R2 tends to R2 minus R3, so that the simplification will become easy. So if I apply R1 minus R2, it will be 0, minus 1, minus 2. Similarly, R2, 0, 0, 3 minus lambda, 1, 2, lambda is equals to 0. Now, instead of expanding horizontally, what we do is we'll expand vertically, so that the simplification will be easy. That means we need to expand only 1. So if I expand along 1, it will be minus times of minus 1 into 3 minus lambda minus minus 2 into 0, that is equals to 0, which implies 3 minus lambda is equals to 0, which implies lambda is equals to 3, which is option A.
For the block diagram shown below, the limiting value of K for the stability of the inner loop is found to be in between X and Y. The overall system is stable if and only. See, for the inner loop characteristic equation is S minus A, S plus 3A, S plus 4A plus K is equals to 0. For the outer loop characteristic equation is similar except k is replaced by 2k because it is going to be added twice because of the feedback is going to be repeated twice. So if k is in between x and y, 2k is between x and y for the outer complete system to be stable. So k should be x by 2 greater than less than y by 2. Hence option B is correct. What path transfer function of a unity feedback system is? Here the given transfer function is nothing but an open loop transfer function whose pole locations are at s equals to 0 and plus or minus 1. Similarly, zeros are located completely in the left half of the S-plane, that is s equals to minus 5, minus 3. Whereas out of 3 poles, 1 pole is located on the right half of the S-plane. So if we plot, this is 1, this is minus 1, this is 0. Here minus 3, minus 4. So the odd portion, the portion of the root locus is going to lie if the number of poles to the right side of number of poles and zeros to the right side of it is odd number. So this is going to be in the root locus, as well as this is going to be in the root locus, as well as this is going to be in the root locus. So this moves in this direction. There is one breakaway point as well as one break-in point. So the root locus is going to be in exactly symmetric about the real axis of the S-plane. So this is the root locus corresponding to this forward path transfer function. The 4:1 mux below implements the Boolean function which is shown below. The inputs to I1 and I3 is here. If you want to solve, see, out of the 4 variables, 2 variables are connected to the control lines. So what we will do is, by using K-map, we can easily handle this one. See, let's see WX YZ. So this is 0 0 0 1 1 1 1 0. So this corresponds to I0 line, this corresponds to I1 line, this corresponds to I3 line, this corresponds to I2 line. So after substituting or entering the given minterms, that is 4, 5, 7, 8, 10, 12, 15. Here from this I0 equals to 0, so it is already given in the question itself. So we have to find out the I1. So I1 is nothing but this is 0 0 0 1 1 1 1 0. So look at this row, this particular row. Exactly I1 is, if you combine these two things and these two things, you will get it as, it is nothing but y bar plus z. So I3 comes to I3 here is y exclusive NOR of z, and I2 is nothing but z bar. Hence y bar plus z comma y exclusive z. Hence, see here it should not be there. So option C is correct.